Welcome to Lecture 6 in Climate Science course. Um, we are going to be talking about why the Earth is warming. This subject lends itself to getting complicated very fast. I have refrained from I've refrained from showing a lot of math or models as much as I could and still motivate causes. The idea here is to think about what evidence there exists, and what I've done is to tell you about what models are out there and how we use them in various forms of inquiry to get at the idea that greenhouse gases are the primary culprit, if not the only one. And I assure you they're not the only one, but they are certainly the largest player, at least as we understand it today. And try and avoid some of the complexity. So we're going to get into this pretty quickly. So we're going to plow right in here after seeing this beautiful picture of the atmosphere. So we want to evaluate the various factors that affect the climate and decide if we understand what's going on. You'll remember this picture. This is a picture that shows the temperature variation, increased temperature by around the globe. So the uneven increase in temperature, especially in the North Polar region. The only way the Earth can get warmer is if there is a radiation imbalance, as we've said a few times in this course, that more energy has to be coming into the surface of the Earth than is leaving. And we know that that positive imbalance has to start with the sun. And this picture shows an accounting of the energy budget for the Earth, if you want to think of it that way. It looks a little complicated, but actually we have set the stage for a lot of these factors. And so I'll go through this a little bit. You can see that incoming solar at the top of the atmosphere before reflection is about 340 watts per square meter. Again, we're using this unit of watts per square meter, which is actually energy per second per square meter, right? Some people would call that power per square meter, but we're just stick with energy per second per square meter to keep it simple. So of that 340 watts per square meter that comes in from the sun, some gets reflected and some makes it to the surface. So some gets reflected off the surface, some gets reflected off clouds, and some gets absorbed by the atmosphere. We talked about the absorption on the way down. You know, remember I said in the visible part of the spectrum, the Earth's atmosphere is fairly transparent to the energy coming in. However, there are some lines supplied by some molecules that absorb some of the energy at those shorter wavelengths that come from the sun. Some energy gets reflected off the clouds. Some energy that makes it to the surface gets reflected by ice and all the different parts of the surface. So what actually gets absorbed at the surface is 161 watts per square meter. So this is equivalent to about 3 60-watt light bulbs. And obviously that's the energy that we use. Now, as the surface heats up, there is water that's evaporated. That is carried heat that goes up into the air. There is what's called sensible heat. That just means there's convective heat, that energy that's carried up into the atmosphere by convecting air into the atmosphere. And the Earth's surface radiates infrared energy or heat energy out of 398 watts per square meter. Now, the first thing people think of is why the 398 is bigger than the 161. Well, that's because a lot of the energy that's radiated away from the Earth comes back down because it goes up, it gets caught in various greenhouse gases and is radiated back down. As you can see here, 342 watts per square meter comes back down. And what escapes is the 239, right? And you'll notice that if we stay at the top of the atmosphere and just draw a line in your mind across where it says TOA, top of atmosphere. If you take the 340 and subtract 100, because that's just reflected back into space, what goes down is around 240 and what comes back is around 239, which says that the Earth is pretty much in balance, right? It's only out of balance by a small amount. You also notice on this graph that there are variations, in parentheses. So again, go look at the 340, I'm sorry. Look at the 340, it says 340, 341. What that means is there's some range of energy from 340 to 341. And if you look at the other numbers on this graph, you'll see that they have large ranges. I'm not large, but they have ranges, right? Those ranges are bigger than the imbalance, right? So this just says it's very difficult to actually create a measurement. Or another way to say that is, first of all, it's difficult to create a measurement at the top of the atmosphere that could get this down to a fraction of a watt per square meter. But also, there's a lot of variability in these things. If you get more clouds, you get more reflectivity. If you can understand that things vary, the amount of evaporation varies around the globe at different times on different days, right? But these are round numbers to give you a feeling for what might be going on. And this is from a National Climate Assessment Report in 2017, although these numbers are still considered representative of what's going on here. We know, because in the previous session we argued that the Earth was warming, we know there has to be an imbalance. But what we're saying is that while we can put, pretty good estimates on some of these numbers, it's very difficult for us to actually measure the imbalance. Now, there are some more recent satellites at the top of the atmosphere that are trying to do measurements at the top of the atmosphere to get at measuring the imbalance to less than a watt per square meter, but that is going to be a future measurement, not available today. But one thing we can do with this is we can develop an approach to thinking about what's causing the problem by saying that let's transfer the problem from the question, what's causing the temperature increase, to what's causing an energy imbalance. And you'll see why that's useful. It's going to be useful because it's going to be possible for us to make simple models that break up the problem into smaller problems and ask the question, if we did this, how much energy imbalance would we get, right? So it might seem like changing the question from what's causing the temperature increase to what's causing an energy imbalance increase that we know has to be there, although it's difficult to measure, isn't a big improvement, but in fact, it turns out to be. So what we're going to do as we go forward is we're going to talk about three different approaches to this problem. One is kind of circumstantial evidence. The next one is an approximate approach using this energy imbalance method. And the third one is to get serious and sit down and make a model for the whole global climate, right? And you have probably heard about these models, global circulation models, various kinds of global climate models. And we're going to talk a little bit about those as we go through this and what they reveal about the temperature increases that we're seeing. So let's begin by talking about some circumstantial evidence. So if you were a detective and you were investigating a crime, you might say, who's at the scene of the crime and what is their motivation, right? That's a standard technique. If we've all watched enough detective TV to kind of ask those two questions, right? Well, what we know is that if we look at the CO2 concentration since, let's say, 1960, the graph I have here, and the temperature. So I have plotted on the graph to the left the CO2 concentration in parts per million, and on the leftmost scale, vertical scale, is that parts per million. On the right scale is the temperature, right? And of course, if you just look at these numbers, you would say, wow, the CO2 is going up and the temperature is going up, okay? A more sophisticated thing to do is the graph on the right. On the right, I have done what is called a cross plot. In other words, I've taken a point, a year, these are years, each one of these dots is a year, and I've said, what is its CO2 concentration? And then what was the temperature for that year, the average temperature for that year? Again, this is over the same range, 1960 to the present. And you get a scatter plot. And if you fit a line to this scatter plot, what's called a least squares fit or a regression analysis, you'll notice that there's a very strong correlation. That's what a statistician would say. These two variables are obviously correlated. And in fact, there's a measure of that correlation. And you see up at the top of the graph, there is the equation for the line, y equals 47 point something times x minus 2,392. Below that is an r squared. R squared is essentially the difference between the line as some measure of the amount of distance between the line and the points for all the points summed together, right? And the idea is if these two variables were perfectly correlated, that is, if the CO2 and the temperature fell exactly on the same line, then we'd say there's some kind of physical, there has to be some basic relationship between these variables, right? What you get for this r squared is a value 0.897. Actually rounded would be 0.9, right? That is a very high r squared. If you look at the r squared, for example, for smoking related to lung cancer or other kinds of things like that, they're much lower, right? So what this tells us is that whatever theory we have for what's causing this temperature increase, it has to explain why CO2 is changing, right? If you want to think of this in circumstantial evidence, go back to the detective story. What we're saying was CO2 was at the scene of the crime. Now, that doesn't mean CO2 did it, but what it means is the CO2, what's going on with CO2 and temperature has to somehow come out of whatever explanation we have, right? Now, if we go one step further, we remember, because we went over this in lecture 1, and we've referred to it a couple times since, we can go one step further about CO2 and some of the other greenhouse gases when we look at it and say, we understand the greenhouse effect, and we also understand the role that CO2 plays in warming the Earth's surface. And so this would be like, what is the motivation? What reason, what motive would a person have for committing this crime, right? Well, I realize it's kind of worn analogy here, but let me proceed. But the idea here is that we know CO2, actually what it does, together with other greenhouse gases like methane and water. We know that these molecules absorb infrared energy leaving the Earth, trap it, send it back down, and warm the Earth's surface. And they warm it by some 60 degrees, right? We also know that CO2 is the biggest player in that story, right? We haven't talked a lot about that, but you can tell just looking at this curve that CO2 is taking a very big chunk out of the emission spectrum of the Earth's surface, right? So as a consequence, we can say, again, there's a CO2 is not just well correlated, but it also is a greenhouse gas that we know has a big effect, right? Now, one of the questions that comes up when people think about this, these two effects, so this circumstantial information that I'm giving you, evidence if you want to call it that, is that if you look at that CO2 curve, that CO2 line, I should say, in the emission spectrum. So go to where, look along the top wavelength where it says 14, 15 microns, look straight down, you see the big divot that CO2 takes out of the emission spectrum of the Earth. You know that having taken that divot out, the rest of the emission spectrum, the surface has to heat up, the surface of the Earth has to heat up to compensate for that divot. What it says is that you look at the bottom down there and follow the 220 dashed line. And what it says is when that energy that left the Earth's surface at 15 microns actually gets emitted into space, it gets emitted where the Earth is 220 degrees Kelvin. That is about up at 8 to 9 to 10 kilometers, right? Up in the, where it's much colder. That's why the spectrum, the emission spectrum, is much lower in energy because it's emitting energy to space at a much colder temperature. Now, a lot of people look at that, and we know this as well, that CO2, the CO2 line, you might add, if I add CO2 at this point, how much higher can that go? In other words, you're already getting close to the top of the troposphere. So the way scientists talk about that is they would say the CO2 line in this spectrum is pretty much saturated. What that means is, it doesn't mean that if you add CO2, there won't be any effect. But it means if you add CO2 to the atmosphere, the effect is not going to be linear with the amount of CO2 you add. For those of you who know a little math, the effect is going to be logarithmic. That is, another way to say that is if you double the CO2, you get an effect. If you double it again, you get the same size effect. You're only going to get saturated increases. Now, it turns out there are models that tell us a little bit, tell us a lot about how much that increase will be, and we're going to get to those. But that is one thing to understand about this that says, yes, CO2 has to be explained, and yes, CO2 is a disturbance that has raised it 60 degrees Fahrenheit, but it's also, we've got a lot of CO2 in the atmosphere, and we're also saying we're not going to get a huge effect out of it, right? And now we have to talk about what huge means, of course, and we're going to be working on that as we get to the next step. So now let's think about, now that I've given you that circumstantial evidence and the little caveat about the saturation of the CO2 line, let's think about what else could affect the temperature of the Earth. So here's a bunch of things. Obviously, there are other greenhouse gases other than CO2. There is methane, H2O, which is water, nitrous dioxide, and others have all been increasing, mostly driven by human activities. Water, of course, not driven by human activities. Water is also a greenhouse gas, and when you increase the temperature, you increase the water. So we will talk later about how that is a feedback effect. In other words, if you take what are called these dry greenhouse gases like CO2 and methane, you put them in the atmosphere, as a consequence, you raise the temperature, you then get more water in the atmosphere, and that in turn raises the temperature. We saw that the increased temperature increased the absolute humidity, or we actually plotted the specific humidity, the grams of H2O per kilogram of air. And we showed that that has been increasing. And so that's an important part of this first indication here. Secondly, we could have increases or decreases in the solar irradiance, the energy coming from the sun. The sun is a middle-aged star. It does increase its intensity slightly over time. The more common thing that we see with the solar irradiance is the 11-year cycle. Some probably should be called the 22-year cycle, but we won't get into the details there. At any rate, we know that the sun goes through an 11-year cycle, and its energy goes up and down in that 11-year cycle, right? And the question, of course, is how that affects what we see. Now, of course, what we see is not an 11-year cycle. What we see is a steady increase in the temperature measurements. But we'd like to know the role that the sun's output plays in the warming. Then we have the role of aerosols. Aerosols are small particles. They can be liquid or they can be solids that are suspended in a gas. So when you shake up an aerosol can of paint, you're actually suspending liquid particles in the gas that's in the can, so that when you spray, the liquid particles come out in the, sort of driven by the gas in the can. These small particles, from very small, 1 nanometer, which is 10 to the minus 9 meters, all the way up to 20 microns, play a very complicated role in the atmosphere. Certain of them just scatter light around. Some reflect light, some absorb light. But one of the most important roles they play is they act as condensation nuclei for clouds and small droplets. You may know that for water to condense, it likes to have something to condense on. It needs, the condensation process requires the water molecules to arrange themselves in a certain way. And they have a hard time doing that in free space. So typically, water vapor likes to condense on a surface. And these aerosols play a big role in providing surfaces for water to condense on. And as such, they end up playing a big role in the formation of clouds, which, as we've said earlier, reflect sunlight, so they reduce the amount of sun coming in, which could cool the Earth, which does cool the Earth. But they also emit infrared energy from the Earth back into space, and so it's a complicated relationship, and we're going to investigate that a little bit further. Because we have 7.7 billion people and we're doing things to the Earth, we have changed the way the land is used. If you're flying in an airplane, you look down at the Earth, you see agricultural farmlands, you see some forests, but you also see forests that have been removed, and so on. There's a lot of changes to the surface. Cities show up in certain ways, and so on. Those changes have an albedo effect. That is, the reflectivity of the surface changes, and we reviewed in the first lecture how the albedo of a forest is a lot lower than, say, the albedo of a desert, right? Another factor is airplane contrails. These are those, when you look in the sky, you see line-shaped clouds formed from jet engine exhaust. And you might say, gee, is that really such a big deal? Well, it turns out that there's a lot of them you don't see up there, and they do make a difference. And they actually absorb energy. They reflect and absorb energy from the sun. And if there are any recent volcano eruptions, they put a lot of particles and dust and sulfur dioxide into the air that absorbs energy and scatters it. In fact, when Mount Pinatubo blew up back in the 1990s, I think, there were a couple of days when the Earth cooled off. And then, of course, the other thing volcanoes do is they send out more CO2. So you get an initial cooling, then a contribution of CO2 to warming. And if you go back to some of the climate changes that led to mass extinctions, back when the Earth was highly active, some of those were caused by large volcanic eruptions, not a single volcano, but a whole bunch of them erupting at the same time when continents were smashing into each other. So these are what you might call the independent variables. And you might ask yourself the question, is this all of them? Well, when I say independent variables, what I mean is things that come into the system in terms of from the kind of independent of the system itself. When we start talking about other variables in the climate, of course, there's a whole lot of them, but those other variables are caused by these. That is, those other variables are in some dependent relationship in how the climate's built, how the climate essentially circulates energy, moves energy around, balances itself. And those variables are internal to the system, whereas these variables you can think of as external to the system. So let's proceed with that idea. So we want to introduce a new name, a new term called radiation imbalance factors or radiation factors. Actually, what you'll see in reports and in papers, publications, are scientists will talk about radiative forcings, right? And all you have to remember is that it's all about this imbalance at the top of the atmosphere. So if you look, for example, at the CO2 at the very top of this graphic, where it says CO2, you'll see a red bar to the right. And the red bar goes on a horizontal scale. If you go down to the bottom of the same figure, the scale is in watts per square meter, right? Back to our favorite joules per second per square meter. And what this says is the radiative forcing, or the amount of imbalance the amount of imbalance that you would get from the amount of CO2 increase we've had from 1750 to 2011 is that number, which looks to me, just looking here, like maybe 1.7 or 1.8 watts per square meter, right? And then below that, we have the other WMGHG, which just says the other well-mixed greenhouse gases. Scientists don't like to write the words out, and it wouldn't fit in that little space. But you can see in that red bar there, CH4, N2O, and various halocarbons, and their contribution, right, to the top of the atmosphere, to basically to the radiation imbalance at the top of the atmosphere. We say the top of the atmosphere, that's how these things are calculated, because we're measuring how much is coming in with respect to how much is going out, right? So that's the place that you can do the math the easiest. So you go down this curve, and I will go down this graphic, and I will. Over on the left is basically the forcing agent. In other words, what is causing the radiative forcing? And on the right is a bar that shows the colored bar, which shows the amount. And then there is an error bar in each one. In other words, there's a estimate of how wrong we could be. And so you can look down here and see the contribution from CO2, from the other well-mixed greenhouse gases, from ozone in the stratosphere, has a cooling effect, that's the blue bar. Ozone in the troposphere has a warming effect. We saw that ozone line in the emission spectrum of the Earth. That's the red hatched bar. Stratospheric water vapor from methane, that's a complicated one, but basically methane can end up making water vapor in the stratosphere. That's a red bar, it's small. Land use, a lot of the land use we've done is actually cooling. So you see the surface albedo there is cooling. There is an effect from black carbon that is sent out from coal plants and other burning of fossil fuels and ends up landing on ice, like in Greenland and other places, making the surface darker, right? And that, of course, makes it more absorbent. And so there is a surface albedo effect from black carbon that basically subtracts from the land use effect. Some people are sort of surprised that the land use effect is cooling. And that's because we've replaced a lot of forests with a lot of dirt, soil, farmland. And the farmland is less absorbent, more reflective than a forest is. Contrails are somewhat warming, very small effect. And then there are two big cooling effects, and both of these have rather large error bars on them. One is what's called the aerosol radiation interaction. This is just that we make aerosols that absorb energy and reflect it, right? And so they interact with the incoming energy in such a way that they do that. And then there's the aerosol cloud interaction. This comes from the fact that aerosols are very good at condensing water vapor and act as cloud generators, if you want to think of it that way. You have to have moisture in the air to a certain degree. You have to be less than or approaching the saturation pressure. But, you know, just like people used to talk about salting the atmosphere to make clouds with dust and stuff. Well, that's what you need. And these aerosol, we judge the cloud interaction as negative. Now you will see later, I'll show you a reason why it can be negative or positive, but we currently believe it's negative. Now the consequence of all those, oh, sorry, I left the solar one out at the bottom. The solar irradiance is at the bottom, and we judge that to be slightly warming. In other words, even though there's an 11-year cycle, there is a longer range, slow increase in the intensity of the sun. It's obviously very slow, measured on the timescales we're talking about, right? And so there is a slight warming due to the sun. Now, if you look at the total anthropogenic, which means basically caused by man, if you look at the total amount, it's a little over 2 watts per square meter, maybe 2.2, but a very large error bar that goes all the way down close to 1 watt per square meter and all the way up close to 3 watts per square meter. Now, where do these forcings come from? How do we get these forcings? Basically, we get them from various independent models, right? So we have various kinds of models. I'll give you an example in a minute that say, hey, if you add this much CO2, you will get this kind of imbalance in energy at the top of the atmosphere. And these are independent models. In other words, they don't, you know, the land use is based on how much we believe the albedo change, taking pictures of the Earth, and so on and so forth. These models they're not a global climate model. These are different. So we're doing this somewhat approximately in the sense that we're saying you can add up the results of these models. That's the approximation, right? We're saying if CO2 creates that much imbalance at the top of the atmosphere, and ozone does this much, and land use cools this much, and aerosols cool this much, we can just add up those watts per square meter at the top of the atmosphere. It's a simplified assumption that they add up linearly and they're not dependent on each other, right? And we know that's approximate, but it gives us a very good feel for what's going on. So to summarize, changes in these various independent variables are estimated over a time period. So we know from 1750 to 2011 what's been happening with CO2, land use, aerosols, and all these other things. And what we're saying is by taking various models of how those things affect the radiation leaving the Earth, we can estimate the total radiation imbalance at the top of the atmosphere with some accuracy, but a pretty big error bar, right? What it tells us is that the greenhouse gases are a very important contribution to warming. They're not the only ones. Ozone is there. The sun contributes a little bit, but the big ones are the greenhouse gases. This is one approach to this problem of looking at it. Now, let me just spend a second sort of showing you one of these models. So this is from a model called MODTRAN. It stands for the Moderate Resolution Atmospheric Transmission Model. I'm sure yeah, not important to remember that. It is a model, I believe today it's owned by the Air Force, but I think it was first developed by Caltech. But you'll notice that the green, so look at the CO2 line. Now we've become so used to looking at the spectrum, we can see the CO2 line. And you see some green on it, right? The CO2 line at 300 ppm is green. And this model calculates that at 300 ppm, we should see a outward flow of infrared energy of 260 watts per square meter, right? If we take this model and just increase, and by the way, we can take that outward flow and we can take the 300 ppm, we can calibrate it against the real emission spectrum from the satellite, right? Now, and then if we calculate the same model with twice that CO2, which gives us an outward flow of we get an outward flow of 256.72 watts per square meter, right? And that says that the forcing agent is the 3.39 watts per square meter, right? Now we obviously are not now at 600 ppm CO2. This is just to illustrate how this model calculates a number. Notice what's happened to the line. It's gotten a little wider and only slightly deeper. Remember, we said it's going to be hard to go higher in the atmosphere, which would be colder, which would mean you get less energy emitted out of that line. So it's wider, and this kind of what's called line broadening, the way this line gets wider, is a well-known effect in emission spectra of all types. So this model has allowed us to do a calculation for the effect on the top of the atmosphere, on the imbalance at the top of the atmosphere, right? Now we're getting a much bigger number here, remember, because we're going to 600 ppm, and on the previous graph, we were just taking what happened between 1750 and 2011. That was 280 to maybe in 2011, 400 ppm. All right. So that's how you get these models, and I won't go through all the different models for all those different effects. Some are quite complicated. Some get into statistical zones. For example, with aerosols and cloud formation, there's not a calculation you can do that is just based on equations. You have to bring into account statistics. What is the distribution of the aerosols? What is the distribution of moisture in the atmosphere? And it gets a little harder to, it's a semi-empirical kind of calculation. Okay, now, clearly what we've shown here is other gases are important other than CO2. Here's, even though CO2 represents 65 or 70% of the emissions in the atmosphere, the next biggest one is, I'm sorry, more like 75%. Carbon dioxide from fossil fuel is 65%, but carbon dioxide is also released by forestry and land use, where we cut down trees and so on. Methane is a big player at 16%, nitrous oxide. And then we get into other gases. They're called F gases here because they're fluorocarbons typically that are the biggest contribution there, right? And if you look at a table, you will see in graphs and so on that I show in the future something called CO2e or CO2eq. So if you look over to the right, there's a table there of CO2eq, right? And it starts at 386, and at the bottom of the table in 2015 is 485. If you go over to the left, you see the years, and you see next to those, CO2 has an effect on watts per square meter. So this table is in watts per square meter, and it's saying that in 2015, the CO2 all by itself created 1.938 watts per square meter, right, of imbalance at the top of the atmosphere. CH4 about 0.5 in 2015, and you can read across there and see the importance of these other gases. So N2O is 0.19, 0.165 for CFC12. CFC is chlorofluorocarbon. 12 is just a particular molecule, and so on. So you get a total imbalance over to the right of 1.76 in 1980 and 2.97 in 2015, right? And those correspond to a CO2 equivalent. And the reason we do that is because we want to make graphs later on of the total emissions that are influencing temperature, and we're going to use, we're not going to have, although we're going to put in numbers for all the different gases, we want to use one number to talk about the effect. And so we use CO2 EQ. So I wanted to introduce that measurement here and how we do it. We do it by calculating the individual watts per square meter at the top of the atmosphere, adding them up, and then saying how much CO2 equivalent would that be. And you see that it's 485 in 2015, even though in 2015, CO2 by itself was probably around 390 to 400 parts per million, not 485, right? Okay, so let's look at albedo. And I showed you a table earlier on about albedo. And we will just say here that the albedo, if you look at this, you see, and the left scale is in percent. You can see that snow, fresh snow is, as high as 85% reflective. Old snow is down in the 50s and 60s. Cumulus clouds are in the 70% range, stratus clouds in the 50%. You go up to cirrus clouds, they're in the 50% range. And if you look at deserts, they're like closing in on 30%. Dry soil is at 30%. Forest is way down at 10%, right? Centered around 10%. Dark soil is 10%. Water is very low, below 10%. So when you replace ice with water, like when the Arctic ice melts and you go from a bright fresh snow to water, you're going from 80% to less than 10% in albedo. When you replace forest with desert, you're increasing albedo. You're going from 10% to, let's say, 28% or some number like that. And then clouds are pretty reflective. So clouds are going to cool the earth, right, is what we expect. So let's move on to clouds. And what we see with clouds is it's actually a little bit complicated in that low clouds tend to absorb a lot of energy from the Earth's surface, and they, of course, re-radiate it in all directions, some of it back down and some of it up. But low clouds also are very reflective. So if you look at cumulus clouds or stratus clouds, you get a lot of reflectivity from those clouds. If you've flown an airplane and it's a cloudy day and you go up through the clouds and you pop through the cloud layer, suddenly you'll notice out your window how bright it is out. A lot of energy is being reflected off the cloud surface. And that leads to cooling. The fact that the clouds capture infrared radiation from the surface and re-radiate it in all directions leads to warming because some of it comes back down. So the bottom line is that typically cirrus clouds, which are way up in the sky, and they form and condense on aerosols, typically mineral type aerosols, very, very small ones that get that high up. They tend to reflect energy away as well as absorb what's coming up. So the basic rule of thumb here are that low clouds warm and high clouds cool. And because the reason that high clouds cool is they're usually thin and wispy, so they pass most of the sunlight through. but they do absorb infrared coming from the Earth. Low clouds are usually water droplets. They're thicker. They tend to reflect more sunlight, and they do radiate more infrared energy at higher temperature because they're closer to the surface. So even though they scatter energy, infrared energy around, because they're close to the surface, they're re-radiating that energy back up at a higher temperature, right? So meaning there's more loss of energy because it's at a higher temperature. So low clouds cool and high clouds warm. And there are many more low clouds. That's why the aerosol effect is considered a cooling effect. This is the solar irradiance over an 11-year period. And you can kind of see that we don't see a long range effect here, but we do see this sort of effect. And you'll notice that it's relatively small. It's about, even peak to peak for the 11-year cycle is, you know, let's say a watt per square meter. What's interesting about this kind of disturbance is you can see, you can look at it and say, if it produces a watt per square meter of change in energy, then can we figure out how that affects the temperature of the Earth? And there's some rough ways to do that, which gives us a chance to sort of say, how much does an imbalance of that amount at the top of the atmosphere, sort of 1 watt per square meter, what would you multiply that by in order to get the temperature effect? Going back from imbalance at the top of the atmosphere in watts per square meter back to a temperature, because originally we said let's change the question from what's changing the temperature to what's changing the energy balance at the top of the atmosphere. If we know the energy balance at the temperature at the top of the atmosphere, wouldn't we like to compare that to the temperature increase? And of course the answer is yes, but it's hard to do that calibration. Here's a way to do that. Now it's been done other ways as well. Admittedly, these are rough numbers, but it comes out about 0.8 degrees centigrade per watt per square meter. You'll notice that we have seen in the temperature measurements, the instrumental temperature measurements, about 1 centigrade increase in temperature since the industrial age. So that says that if this number that you multiply the imbalance with is, let's say, around 0.8, that says the imbalance is a number like 1.2. So 1.2 watts per square meter. At any rate, those are round numbers because those are difficult estimates to make. Now, we also have some other information that suggests that even though we've made the measurement, which is much more convincing, originally when people started looking at the sun as a possible cause of the warming that we're seeing, what was noticed was that there are more warm nights. If you look at the warming, it's happened more at night than during the day. And it's not that we don't have more warm days, we do, of course, but, and we have less cold days. But the frequency is also true that we have a lot of cold nights, a lot less cold nights and a lot more warm nights. And what that means is that whatever the sun is doing, it's on the wrong side of the Earth for the night effect, right? And so it's not likely that the sun could be the cause of this, because you would expect during the day, we would see the big increase in warm days and a bigger decrease in cold days. But in fact, we're seeing the same or even increased effect at night. Okay, so now I'm going to give you just a couple of notes here on how to get back to temperature. So as I said, there is this idea, the scientists give it a name, the transient climate sensitivity. It says if you change the radiative forcing, the total number, remember that was the number at the bottom of the screen, about 2.2 with a large error bar. If you change it, then there is a constant called lambda, which is about 0.8, and that constant is measured in 2 or 3 ways, but they all have uncertainty associated with them. You would get a change in surface temperature of 0.8 times 2.2, which is about 1.6 degrees Kelvin, which is the same, since it's an increase, it's same 1.6 degrees centigrade. Coming from that imbalance. Now, what we've actually observed is about 1 degree centigrade, as I said earlier. That either means that the imbalance is actually 1.2, or that the Earth is warming up slowly, and we're going to get 1.6 out of what we have, right? Out of the CO2 that's already in the atmosphere. That comes from the idea that if you turn your oven on and you set the temperature, it doesn't warm up immediately, it takes time. So in a sense, the increase in whatever's causing the radiative imbalance is basically the burner element that's warming up, and it's going to take time. And so this 0.8 is estimating something that's still yet to happen, right? The other way to get to this estimated change in the surface temperature is to ask, let's build a full-scale climate model. And what I mean by that is one that reproduces all the circulation effects, one that takes into account the cryosphere, one that takes into account the biosphere. And let's calculate, if we doubled CO2 using one of these really large models, what we would get. And if you look down below, the graph down below is a whole range of different model simulations. And 2 things happen in here. These are different models and they are different simulations, meaning they have different inputs. All assuming a doubling of the CO2 equivalent. Now I'm using CO2 EQ here, meaning all the greenhouse gases, an effect of all the greenhouse gases. No matter what proportion each of them might contribute, it's a doubling of the CO2 effect. You get numbers from 2 degrees up to like 6 or 8 degrees, although today we don't really believe those numbers at the end. This was a 2013, I think, IPCC study. More work has been done since then. And we would say for a doubling of CO2, now this would be 280 ppm. You remember that was the peak of the glacial, of the interglacial warming periods that we've seen over the last 3 million years. If we doubled from 280 to 560, we would get something like a minimum of a 2 degree C change all the way up to maybe a 4 or 5 degree C change, okay? Based on these various really complicated climate models. That agrees roughly with our rough estimate of what we got out of the radiative forcing. So what I've described for you is 2 ways to get at an estimate of future climate prediction. One using the radiative forcing and this rough idea of estimating lambda, and the other making a very complex model, right? And I just want to say in the next, I'm going to skip that. In the next section, when we start talking about these climate models, there are different timescales for how changes affect the temperature, right? So if you look at this, when you inject 2 times the CO2 equivalent into the atmosphere, clouds and water vapor adjust fairly quickly. The upper ocean warms up a little more slowly. The atmospheric composition changes fairly quickly. These are years, not even quite to decades. The upper ocean takes decades to warm up. CH4 takes decades to decay into CO2. Vegetation on the Earth takes a long time to change its nature, move to a place where it's comfortable, if I can say it that way. We know that things move around the Earth based on temperature. plants adjust. The oceans, circulation takes maybe thousands of years. The ice sheets take many thousand years. And the carbon cycle adjusts over an even longer time frame, right? That is the way carbon gets sequestered. To return carbon back to the Earth in a stored way takes many thousands of years. We saw that in the Paleocene-Eocene thermal maximum, where the carbon pulse from that event took 100,000 years to decay back to normal. So when you make one of these models, these effects come in at different times, right? Now, so these real climate models, I'm going to spend a little bit of time on these real climate models, only a little bit. I'm only going to tell you a couple things about them. What I suggest is there is a very good TED Talk by a fellow by the name of Gavin Schmidt, S-C-H-M-I-D-T, on climate models. It has some video in it of climate models in action, and he tells you kind of the state of the art. So if you go to Google, just search for climate models, Gavin Schmidt, or just do Gavin Schmidt TED Talk, and you'll get his TED Talk on climate models. So we're going to say just a few words about them here. Basically, what's very important in these models is feedback in the system. We talked about the fact that if you increase the temperature, the air holds more moisture, and that means it holds more water vapor, which is itself a greenhouse gas, and that raises the temperature. That's a feedback effect. It's actually called a positive feedback effect in the sense that the temperature increases causes something to happen, which causes the temperature increase. So it's positive in the sense of moving in the right direction. You may not think of it as positive in a good sense, but that's what it is. Also, increased temperature leads to more condensation of water vapor into clouds. And we know that low clouds cool on average. So you might hope that the clouds would help save us. If we got more low clouds, we might get some cooling from that. That would be a negative feedback. The temperature increased and we got a cooling. However, that balance is unclear with what we've got today in these models. It looks like the clouds may move around a little bit, which may compensate for, what I mean by move around is move to other latitudes, move further north. So that one's still being worked on. However, we still think clouds are cooling, and some of this may be a cooling effect. Some of this feedback may be a cooling effect. Increased temperature melts ice, which lowers the Earth's albedo and increases the temperature. So again, that's a positive albedo effect. But as I've said earlier, it takes time for that to happen. It doesn't adjust in years. It doesn't adjust in decades. It really adjusts more in centuries. However, we're going to see later on when we start talking about sea level rise that we have some estimates today that we may be underestimating the effect of the sea level rise. Now, these climate systems take the inputs that we've been talking about, sunlight, greenhouse gases, aerosols, land use, and other inputs, and have models for how the biosphere, the atmosphere, the oceans, and the cryosphere are connected, and the feedbacks that are in those systems from temperature, humidity, and precipitation to predict what's going on in the outputs in terms of these variables spread over the global Earth. That's the idea. So you can tell this is a very ambitious project to make these models. There are probably 10 or so consortiums around the world with the best understanding climate scientists and computer science people, because these are supercomputer type models that run for long periods of time to basically say what's been happening in the climate from 1750, let's say. Over time, these models have evolved. So if you go back to the mid-1970s, we had very simple models that tried to generate some of the circulation patterns that we talked about earlier, the 3-cell circulation in the atmosphere and the circulation in the oceans, the surface currents, the thermohaline circulation. This would contain the rain, the the water vapor cycle. By the mid-1980s, we were able to put in the land surfaces. Remember, we talked about the difference between the land and the ocean in terms of temperature change with time, both during the day, but with the seasons and so on. And in the mid-1980s, we had clouds into the models and ice, the beginnings of ice. Then these things that say FAR and SAR and TAR and AR4, those are reports, IPCC reports that were put out in various years. The AR4 is 2013. The TAR is, I believe, 2008 or 9. But you can see that these models get more and more complicated. We start bringing into account volcanic activity, some of the aerosols, in particular the sulfates that come from power plants. We have the full ocean model now. We have clouds. And later on, we bring in the, we find out that, we bring in the carbon cycle. We bring in water coming from the land. We bring in some more circulation in the oceans, the overturning circulation, which was the thermohaline circulation. Apparently, we bring in a sailboat someplace here. I'm not quite sure why that's there. At any rate, when we also bring in, we find out that the physicists find out that at their university, there are people who study biology. So they actually start bringing in the interactive vegetation, the biosphere, which absorbs carbon dioxide and emits it depending on the seasons and so on and so forth. So these models have gotten very complicated. If you go to carbonbrief.org, you can read some reviews of some of these models. They continue to be improved, and you can go look at the Gavin Schmidt video also. You can see in these models how our resolution has improved over time. So the way they work is there's a grid, and basically inside each of those things that look like little cubes, you have the pressure, temperature, and moisture content, and you basically map those from one box to another with differential equations that tell you how the whole model changes with time, and including the velocity of the winds and the velocity of the currents in the ocean and so on and so forth. This just shows that because of the increases in the ability of supercomputers to compute, we end up with more fine-scale detail in these models as you go from the FAR, the SAR, to the TAR and the AR4. And finally, these are what the models predict. The black line is the average prediction. The different colored lines are the different models from different organizations, different international consortiums. And the light lines on the outside, I think, are the boundaries on these, error boundaries. So you can see that the actual temperature, I believe, is inside that boundary. And so the models are more or less predicting the temperature going forward. One thing I want to talk about briefly is and this is the last thing in this section, is the ENSO. We hear a lot about La Nina and El Nino, which form the ENSO. And basically, the ENSO is an oscillation in the Earth's circulation pattern. It's very similar to something we've talked about before with the sea breeze. If you have cool air off of Peru, and you get, because it's cool air, the pressure is higher there, it forces air to the west out into the Pacific Ocean, where it rises out by Australia. And we get this circulation, like the sea breeze circulation, called, in this case, it's called the Walker cell. And it actually moves water, about 60 centimeters of water, during La Nina. When La Nina is when the ocean off of Peru is cool. The elevation out by Darwin, Australia is actually 60 centimeters higher than near Peru. And I've greatly exaggerated the thermal line, but it's colder to the east and warmer to the west. Now, this switches when El Nino happens. When El Nino happens, it walks back the other way, and so you get this sloshing back and forth. Um, by the way, the ENSO is called the El Nino Southern Oscillation. There are other smaller scale oscillations like this on the Earth, but for some reason the ENSO, because it has a big effect on regional weather, it has become a well-known thing that people, weather forecasters, talk about a lot. So this oscillation has occurred in the system, in the circulation system, and it plays a big role in the weather in southeastern United States and various places on the west coast of the United States. Some have suggested that the ENSO is a cause of warming, right? And I'd like to show you a graph. This is a graph of warming. This is taken from Climate Central, which is a website that has excellent graphics about climate change. If you wish to look at other graphics, they've produced a lot of them. Basically, if you look from 1950 to present, these are the temperatures. Obviously, they're relative temperatures, where 0 degrees is kind of an average taken over the period of time. And the El Nino events are labeled, are colored orange bars. These are annual, each bar is an annual temperature. And you can see, I think it's up to 2015, you can see they're going up. And what you can see is that, yes, El Nino years are warmer on average than La Nina years, which are colored blue. And there are years where it's kind of neutral in the sense that maybe half the year was one way and half was the other, or there wasn't a big effect one way or the other. But what's clear is that the more recent El Nino years are warmer than the ones in the past, and the more recent La Nina years are warmer than the ones in the past. So it's not that El Nino is causing the warming. In fact, the warming has to be caused by some change in the way energy is distributed on the Earth. This is an internal oscillation. So now the Walker circulation that's called, that the ENSO, which is what the ENSO is not generating energy. It is responding to energy that's sloshing around in the system, causing this particular oscillation. And you'd expect that this is also why you get a lot of regional effects, because the circulation is very noisy in the sense that energy moves in different kinds of ways. And this is one way it's very noisy. So the reason I put this in is I wanted to make the distinction between internal variables that are causing temperature, precipitation, and other climate variables to move from external variables that are actually the disturbance in the climate system. All right, so let me summarize here. I think we are asking the question here, can we convict the greenhouse gases as being the cause of the problem? And here's the evidence we can say. CO2 is strongly correlated with temperature variation in the historical record, as well as in the recent times, right? If you look back at what we talked about with paleoclimate, the Cenozoic Ice Age, CO2 does go up and down with the temperature. We directly observe the greenhouse effect and emission spectrum at the top of the atmosphere. We know it's there, and we know it produces about a 60-degree Fahrenheit change because of greenhouse gases, particularly CO2, but other greenhouse gases. We have two ways to get at the cause of this warming. We can look at an analysis of radiative forcings, which is a measurement of the imbalance at the top of the atmosphere caused by a perturbation in something like greenhouse gases or aerosols or other things. And we see that those forcings suggest that there is a large fraction of warming coming from greenhouse gases. Not the only source, but a large fraction. Then we can go one step further with a lot of work over many decades and take these complex land and ocean models and reproduce the time variation of global temperature and learn an awful lot about what's going on in the climate, which builds our confidence that we have a good understanding that greenhouse gases have a principal role. Now, as we go on to the next lecture, we're going to talk about how fossil fuels influence the greenhouse gases and why we think they are a prime contributor to the problem. Thank you very much for joining us.